Hello and welcome to G Fun Facts Online, where we explore the science and technology shaping our future. Today, we're talking about something straight out of science fiction, but it's closer to reality than you might think. Imagine a disaster zone. A building has collapsed, and survivors could be trapped inside. The area is too unstable for human rescuers. Instead of sending one large, clumsy robot, a truck releases a swarm of small, cube-like modules. They spill onto the ground, communicating with each other, assessing the terrain. In moments, some link together to form a long, slender snake, slithering into a narrow crack in the rubble. Others assemble into a stable, six-legged walker, clambering over a pile of debris. This isn't a movie scene. This is the incredible promise of self-assembling modular robots. These machines are about to change everything, from how we rescue people to how we build houses and even explore other planets. So let's dive into the dawn of these adaptive machines. First off, what exactly are self-reconfiguring modular robots? Forget the typical factory robot arm that does one thing over and over. These are chameleon-like systems made of many small, independent units or modules. The magic is that these modules can autonomously rearrange their connections to change the robot's overall shape and function. A pile of cubes can become a snake, then a wheel, then a gripper, all on the fly. This unlocks a level of versatility and robustness we've never seen before, making them perfect for the unpredictable, dynamic environments found out in the real world. To understand how they work, we need to look at their architecture, their fundamental design. Think of these as different flavors of robotic Legos. There are three main types. The first is the lattice-based system. Imagine modules that connect to each other on a fixed grid, like atoms forming a crystal. This structure makes it relatively easy to design the modules and to calculate how they should move to form a new shape. The grand vision here is something called programmable matter. A blob of modules that could form any object you need, like a wrench, and then melt back down and reconfigure into a hammer. The downside? This rigid grid isn't great for fluid movement. It's fantastic for building static structures, but not so good at walking or slithering. That's where the second type comes in, chain-based systems. As the name suggests, these robots connect modules in a series, like links in a chain. This creates snake-like or limb-like structures that are exceptionally good at locomotion and manipulation. A robotic snake that can navigate through a pipe, or a multi-legged robot that can cross rough terrain. These are classic chain-based systems. They offer incredible flexibility. The main challenge, however, is the sheer complexity of planning. Figuring out the exact sequence of moves for a long chain of 50 modules to change from, say, a straight line into a spiral is a computationally massive headache. So if lattice systems are great for structure and chain systems are great for movement, what's next? You guessed it, hybrid systems. Researchers are creating robots that can do both. A great example is a robot called M-Tran, whose modules can form both chains for locomotion and connect into lattices for stability. Another emerging category is mobile-type robots. Here, each individual module has its own little wheels or legs. They can move around independently, find each other, and then connect to form a larger structure. This offers incredible flexibility in how the robots can assemble in a wide open space. At the heart of all these designs are the modules themselves. Each one is a mini robot with its own power, processor, and sensors. And a key innovation is the use of genderless connectors, often using magnets or mechanical latches. This means any module can connect to any other module, simplifying the whole self-assembly process immensely. Of course, a pile of robotic blocks is useless without a brain to tell them what to do. The physical form is only half the story. The true power of these systems lies in the sophisticated algorithms that govern their behavior. The goal is to achieve autonomous self-reconfiguration, meaning the robot can sense its environment, decide on the best shape for the current task, and then transform itself. all without a human joystick operator. This is a monumental challenge. The robot needs to plan and execute a whole sequence of moves. Researchers are tackling this puzzle from a few angles. Some methods break the problem down, using a library of pre-planned moves for smaller sections of the robot. Others treat the problem like a logistics network, calculating the most efficient way to flow modules from their current positions to their target locations. For a swarm of hundreds or thousands of modules, having one central controller is a terrible idea. If it fails, the whole system goes down. This is where distributed control comes in. Each module makes its own decisions based on local information and communication with its immediate neighbors. It's a concept borrowed from swarm intelligence in nature, like a flock of birds or a colony of ants. Simple, local rules, followed by each individual, lead to incredibly complex and intelligent behavior for the group as a whole. And this is where artificial intelligence is becoming a game changer. Machine learning models are being used to help the robot choose the best reconfiguration strategy for a specific task. Reinforcement learning, a powerful technique where an AI learns through trial and error, is being used to develop control software for these swarms. For instance, researchers at Caltech developed a system called GLASS, which uses machine learning to help swarms of robots navigate crowded spaces without colliding, allowing them to learn on the fly. Now for the practicalities. For these robots to be useful in the field, they need power, and lots of it. A robot that runs out of batteries after 20 minutes isn't much help in a disaster zone. Power management is one of the most critical challenges. Relying on batteries that need to be manually replaced just isn't a long-term solution. So researchers are looking at innovative approaches. One key goal is wireless charging, allowing robots to autonomously return to a charging station or even receive power as they move. Even better is energy harvesting, pulling power from the environment. This could be solar power for outdoor robots, or even harvesting energy from vibrations or temperature differences. Just as important as power is communication. It's the lifeline of the swarm. Modules need to share information to coordinate their actions and report back to human operators. Again, the system needs to be robust and scalable. Standard protocols like Wi-Fi and Bluetooth are useful, but Wi-Fi has limited range in cluttered spaces, while Bluetooth is only for short distances. That's why protocols like Zigbee and Z-Wave are promising. They create mesh networks where modules can relay signals to each other, extending the network's overall range. For applications over vast areas, like environmental monitoring, there is LoRa, which stands for long range, offering communication over many kilometers with very low power consumption. Looking ahead, the arrival of 5G and beyond promises the ultra-reliable, low-latency communication needed for real-time control of massive robot swarms. One of the biggest advantages of this modular design is robustness. Field operations are harsh. Robots will face rough terrain and components will inevitably fail. In a traditional, monolithic robot, a single broken part can render the entire machine useless. But in a modular system, the failure of one module isn't a catastrophe. Thanks to redundancy, the system can often continue to function, just with slightly reduced capability. But it gets even better. Researchers are developing robots that can achieve true self-repair. The system can autonomously detect a failed module, eject it, and have a spare module move in to take its place. This is a game-changing feature for long missions in remote or hazardous locations, like on the surface of Mars, where a human mechanic is millions of miles away. So we have these adaptable, intelligent, self-healing swarms of robots. Where are we actually going to use them? The applications are mind-blowing. Let's start with search and rescue. In the chaos after an earthquake or building collapse, time is everything. Modular robots can be deployed into areas too dangerous for humans. As we pictured at the start, snake-like robots can navigate through rubble, using cameras and sensors to find survivors. Fire-resistant robots are being developed to enter burning buildings. The Tokyo Fire Department, for example, already has about a dozen different types of robots in its arsenal. A particularly effective strategy is combining air and ground robots. A drone could fly into a damaged building, drop off a smaller ground robot to search, and then provide an aerial overview. Next up is construction. This industry is ripe for automation. Self-assembling robots could automate repetitive and dangerous tasks, making construction sites safer and more efficient. We're already seeing glimpses of this. Robots like the SAM 100 can lay bricks much faster than a human. The Hadrian X, a truck-mounted robot, can build the entire brick structure of a house in just 2 days. Autonomous bulldozers and excavators are already digging trenches and preparing foundations 24/7. Combine this with prefabricated components assembled with robotic precision in a factory, and you have a revolution in how we build our world. Then there's the final frontier, space exploration. For long-duration missions to the Moon or Mars, sending everything from Earth is incredibly expensive. We need to build things there. This is where modular robots shine, and NASA is funding a lot of research in this area. The concept is called In Situ Resource Utilization, or ISRU, which means using local resources. Modular robots could be designed to excavate lunar soil, process it, and then 3D print building materials for habitats or landing pads. For huge structures like the next generation of space telescopes, it's impossible to launch them fully assembled. Instead, modular robotic arms will assemble them piece by piece in orbit, detecting and correcting errors as they go. On a planet's surface, a rover could reconfigure itself to adapt to the terrain, transforming from a wheeled vehicle on flat ground to a legged walker to climb a rocky hill. Finally, let's bring it back to Earth. Swarms of modular robots could act as a network of environmental sentinels. Imagine deploying thousands of simple, sensor-equipped robots to monitor our planet's health. Drones could monitor air pollution in cities in real time. Aquatic robots could patrol rivers and oceans, detecting and tracking pollutants. Legged robots could navigate through forests to gather data on the health of trees and track wildlife. By monitoring environmental conditions constantly, these swarms could even help us predict natural disasters like tsunamis or wildfires. The road ahead is incredibly exciting, but there are still challenges to solve and big questions to answer. The integration of more advanced AI and swarm intelligence will be critical. We'll also see continued miniaturization, allowing for more complex and high-resolution robots. But we also have to consider the societal impact. The automation of tasks will inevitably displace jobs in sectors like construction and manufacturing. We need to plan for this, with things like retraining programs and creating new jobs in robot design and maintenance. Then there are the ethical considerations. When you have autonomous robots operating in public spaces, what about safety, privacy, and accountability? Who is responsible if an autonomous construction robot makes a mistake and causes an accident? How do we protect people's privacy when swarms of robots are constantly collecting data? These are not easy questions, but they are essential ones we must address as we develop these powerful technologies. In conclusion, self-assembling modular robots represent a profound shift in how we think about machines. We're moving away from rigid, single-purpose robots and embracing a future of modularity, adaptability, and collective intelligence. From saving lives in the rubble of a disaster to building new worlds in the vastness of space, the future of field operations is being assembled, one intelligent module at a time. Thanks for listening to G Fun Facts Online. Join us next time as we unpack another piece of our amazing world.